Okay, welcome back. This is 9.3, the integral test in P-series. Okay. So the integral test, what the heck is that about? Well, basically if f is positive, continuous, and decreasing eventually, the book will say for some x value greater than or equal to 1, and we're representing the terms of the sequence with this function, then the series a sub n and then this integral, and we're going from n equals 1 to infinity here, 1 to infinity of f of x dx. These guys will have the same behavior. Okay. And it's because of the kind of squishy nature of the rectangles when you consider the area underneath the curve, and you go back to the Riemann sums. So recall our work with Riemann sums. We would have some sort of curve, and to get the area underneath that curve, we would populate it with a bunch of rectangles. Okay. Use left-hand endpoints or right-hand endpoints. If you use left-hand endpoints, it would be some sort of phenomenon like this. And you may be wondering, what the heck does this have to do with a series? Well, a series can be thought of as a sum of a bunch of rectangles with base 1. Okay, so if you presume that the length of all of these bases is equal to 1, then the area of the particular rectangles, and what we're doing is approximating the area underneath the curve with the sum of the area of all of these rectangles. Okay. So the area of those rectangles will just be the height of the rectangle times the base. And if the base is always 1, then basically what you have is just a sum of a bunch of numbers, which is basically just this thing here. Right. So you'd have the sum of, in this case, if this is f of x, maybe f of x sub I, or I equals 1 to n or whatever, times the change in width. Usually at the Riemann sum we put delta x, but here we're going to presume that delta x is always just 1. Okay? So if you have a series and a sequence formula and a function formula that are the same, you can replace this thing right here with just a sub I, and basically this sum represents the area of the sum of these rectangles. And then you can compare that to the area underneath the curve. So it looks like maybe the area of these little rectangles would be less than the area underneath this curve. And when I was talking about squishiness, you can always make these rectangles be below the curve or above the curve. And if they're below the curve, and you know that the area underneath the curve is so, well, let's sort of make that. I'll think that out a little bit more here in the next sort of portion of my notes. But hopefully you agree that okay, I can maybe a more concrete examples in order to make this more obvious. So let's compare the sum of this a sub n and this integral from, I don't know, whatever to whatever of f of x dx. Let's let a sub n equal 1 over n, and then f of x equals 1 over x. Okay? So we'll just sum up from 1 to, I don't know. I was trying to think how I want this to work. From 1 to n, okay? Which is a bad choice of variables, of course. Now I have to change this variable so I can have my index go to n. So I equals 1 to n, so I got to change this now to I. Okay, so what is, this thing here? The sum from I equals 1 to n of a sub I is the same as the sum from I equals 1 to n of 1 over I. That's this ugly thing that I had to smush in because I accidentally wrote an n. Okay, that's that. This is equal to 1 plus 1/2 plus 1/3 plus dot 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 plus 1 all over n. Okay. And then this other guy, this integral from 1 over n of f of x, in this case, it's the integral from 1 over n of 1 over x dx. Rather than integrating it, I'll just consider it as area underneath the curve, right? So we can draw this. At 1, it's at 1, so I just sort of screwed myself by putting a tick mark there. So I'll let this be 1 here, just for the sake of the drawing. At 2, it goes down to 1/2. At 3, it's at 1/3. And so it's going to, look like this, and on, all the way up to n, and then this height will be 1 over n. Okay. So the area underneath this curve is equal to this integral. So this area is this thing right here. Then you can re-envision this sum as a sum of a bunch of rectangles such that the base of each of the rectangles is 1, right? Because this thing is literally equal to 1 times 1 plus 1/2 times 1 plus 1/3 times 1, etc. Right? So it's just base times height, or height times base, however you want to think of it. So the first rectangle area is 1. Right? So that's this. Base is 1, height is 1. It should be a square, but the way I've drawn it is a bit off. Then this area of the second rectangle, like that, base is 1, height is then 1/2, right? And then et cetera, et cetera. So the final rectangle, I guess, have to go out beyond to n plus 1. We'll have that area right there. Right? So the deal is, if you know then that this integral diverges, you can, and it won't be a matter of 1 to n, right? We'll take the limit as n goes to infinity. If you know this integral diverges, the area underneath that curve is definitely not going to be finite, right? It's going to be like infinity or something. So if the area underneath this curve is infinity, and we also have that, so let me write this out. If you take the limit of this integral from 1 to n of 1 over x dx, and you find that that's infinity, we can tell just from this picture that whatever the heck this thing is, it's less than whatever the heck the sum of the area of these rectangles is. Okay? And the area of those rectangles will be the limit as we go to infinity, the limit from I equals 1 to n of 1 over I. Okay, so if this thing is going to infinity, it'll kind of force this guy to go to infinity. Okay? And that's the relationship we're talking about. You know, if one behaves one way, it'll force, if this behaves one way, it'll force this guy to behave the same way. Okay? And the squishiness issue I was talking about is the fact that you can either put the rectangles above or below dependent on the endpoints that you pick. Right? So if I know that the integral is convergent, I can always put these rectangles underneath the curve, and that'll have area less than the area underneath the curve, and therefore that sum will be forced to be convergent. And it's a little more technical than that. You have to invoke the monotonic bounded theorem from 9.1, I believe. Yeah, so there's a little more to it than just what I'm presenting, but that's the idea. There's a squishiness of the rectangles. I can either put them on the outside if I know the area underneath the curve, or if I know this integral as I go to infinity is divergent. If I know this integral is convergent, though, I can rebuild this thing just striking off this first term and then thinking of these other rectangles underneath the curve. So I could also envision these rectangles, which would be underneath the curve. Okay. So, you know, it's either one or the other. Either the thing is bounded above, and we have to be a little careful with the indices. Now, I'm going from I equals 2, right? So the first term of this series would be 1/2. But I think we could agree at least that the area of these boxes is less than the area underneath these curves, underneath this curve. So if this is convergent, it'll force this guy to be kind of convergent, because you'll know the area underneath the curve is finite, therefore the area of these boxes is less than that finite area. It must also be finite. And, you know, it's this idea. I can either put the boxes above or put the boxes below. And I will know, because you learned how to do this in chapter 8, you know how to do these integrals. You can figure out if this converges or diverges. And then you can either put the series atop or on bottom, depending on what you want to do. And you'll have kind of your idea panning out there. Okay, so that's the idea. Now you go to the book for the real explanation from the professionals, and let's just dive in here. Okay, so here's number 2. I have the series from n equals 1 to infinity of 2 all over 3n plus 5. Okay, so this looks like something I could integrate, this a sub n expression here. Okay, so that's what I'm going to do. I'm going to consider f of x equals 2 all over 3x plus 5 on the interval from 1 to infinity. It's important to note the interval because to use this, theorem, we have to have the requirement fulfilled that the thing is positive, continuous, and decreasing. Okay. On this interval, if x is greater than 1, we can kind of build the fact that the 3x plus 5 will be greater than 1. Then you have a positive over a positive for all x in this interval, so therefore it will be positive. For continuity, rational functions are only discontinuous where the denominator is equal to 0. The denominator is equal to 0 at negative 5/3. That's not in this interval, so it's continuous everywhere else. And then for continuity, to show it's decreasing, you probably just want to take the derivative. So if we consider f of x equaling 2 times 3x plus 5 to the negative 1, its derivative f prime of x will be negative 2 all over 3x plus 5 squared times the derivative of 3x, which is 3, so it'd be negative 6 over this. The numerator is negative, the denominator will always be positive. In other words, this thing's less than 0. If you remember from Calc 1, that implies it's decreasing. Okay, so we have all three of these requirements holding. On tests, I usually kind of just take these for granted, and I'll probably ask you to prove it's decreasing just to give you some more practice with taking derivatives. All right. Anyways, once you have these three criteria fulfilled, you can go ahead into your integral. So we're going from 1 to infinity of 2 all over 3x plus 5 dx. Okay, so it's an infinite interval integral. So I have to take the limit as b goes to infinity, the integral from 1 to b of, probably want to do a u sub just to be careful, 3x plus 5 du is 3 dx. So dx is du over 3. In other words, there's a fraction of 1/3 to deal with. So we got 2 all over u times du all over 3. And I can drop my bounds momentarily while I evaluate. Limit as b goes to infinity of 2/3 ln absolute value of u. Back subbing, I get absolute value of 3x plus 5. Let's remind myself to evaluate from 1 to b. This will be 2/3, and of course there's still a limit involved here, so we don't want to forget that. It's the limit of 2/3 ln absolute value 3b plus 5 minus 2/3 ln of 8. Okay, the form of this limit is infinity minus L. Okay, so this will go to infinity. In other words, the integral is divergent, and by the integral test, then the original series is also divergent. Okay. Let's keep on moving. It's problem 6. So I have a series from n equals 1 to infinity of n e to the negative n over 2. This one's a little nastier, obviously. Let's go ahead and dive on in. So first I want to show that the thing is continuous, positive, and decreasing. Okay, continuous, n and the exponential, and of course we're considering sort of its function version, x e to the negative x over 2. X is continuous, e to the negative x over 2 is continuous. The product of continuous functions is continuous, so we're good there. Positive, so we have to consider an interval, so we consider the interval from 1 to infinity at first. It'll turn out we have to push out this number 1 to maybe 3 or something, just to make sure the thing is always decreasing. But anyways, is it positive? And certainly x is positive on this interval. The exponential is positive everywhere. So a positive times positive is positive. Clearly that's true. Then finally, for decreasing, again, you can go ahead and consider the derivative. Set it equal to 0. This part will never be 0, but this part will, right? So that's exactly when x is 2. That's our critical number. You do your number line. Here's 2. to the left of it, you try x is 3, so negative 3, that'll be negative. Or actually, it's, if you put in, sorry, if you put in like 0, it'll be positive. Try 3 over here, and then it's negative. So it's decreasing beyond 2, right? So instead of going from 1 to infinity, because of this fact, I'm going to just consider then the interval from 2 to infinity. Right? It turns out if you can always chop off a couple terms and it won't affect the increasing, it won't affect the convergence or divergence of the integral. All right, so let's get to the integral then and take a look. So I'm going from 2 to infinity, x e to the negative x over 2 dx. Okay, it's infinite interval, so you got to rewrite it as a limit going to the problem. And then I have a nasty little integral here. It's pi by parts. So Liate says do the algebraic first. So I screwed that up. Right, so this will be in the limit of this times this. So I'm looking at negative negative 2. Sorry, I got a mistake in my notes, and I'm just worried about it. Negative 2x e to the negative x over 2. That's this times this minus this times this, so that'll be plus 2 integral e to the negative x over 2 dx. Okay, then I can figure that part out. It's going to end up being minus, and then a factor of 2 pops out on top of the 2 that's already there, so we get 4 e to the negative x over 2. We still have to evaluate from 1 to b. Or actually 2 to the b, right? We decided to push out the interval. So you get limit as b goes to infinity of negative 2b e to the negative b over 2 minus 4e to the negative b over 2 minus negative 2 times negative 4e to the negative 1 minus 4e to the negative 1 again. This term here, as b goes to infinity, this thing will just shoot to 0. This thing here will be infinity all over infinity, so it's kind of indeterminate. You can do L'Hopital's. So let's just zoom in on this part a little bit. And so doing L'Hopital's, you'll get negative 2 all over 1/2 e to the b over 2. And then clearly that goes to 0 as well. Okay, so we're left with this constant. In other words, it's going to be convergent to 8e to the negative 1. So if the integral converges, the series from n equals 2 to infinity will converge. If the series from n equals 2 to infinity converges, then the series from n equals 1 to infinity converges. Okay. It's basically if this equals 10 and you add in another number like 1, it's not going to suddenly fly off the handle, right? It's just going to be 11. So the original series converges. at the end of the day. Okay, so a great thing about the integral test is it'll allow us to deal with p-series, which they look a lot like geometric series, but they're not. One of the p-series is called the harmonic series. Harmonic series is 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, etc. It diverges. Okay, so yeah, sure. I'll just note that the series from n equals 1 to infinity of 1 all over n, which equals 1 plus 1/2 plus 1/3 plus 1/4 plus dot dot dot, is the harmonic series, and it's automatically divergent. The rest of the p-series then look like this, 1 all over n to the p. So for the geometric, the exponent, I believe, would be changing. So you'd have maybe 1/2 plus 1/2 squared plus 1/2 cubed. Here it's the denominator that's always changing, but the exponent is the same. And we can call these all p-series, and their convergence and divergence is based off of this p-value. So in this case, the p-value is just 1. Okay? But we can consider these in general then. So let's say this will be 1 plus 1 all over 2 to the p, plus 1 over 3 to the p, plus 1 over 4 to the p, plus dot, dot, dot. And when p is, I always screw this up, greater than 1, it's convergent. If p is greater than 0 but less than or equal to 1, it's divergent. Okay, so the book will try to throw you some curveballs. There's really not much to do with these, but the book's trying to keep the marriage alive. So let's just go ahead and go through the motions here. We got 1 all over n to the 1/2, right? The square root of n is the same as power of 1/2. So clearly the p-value here is 1/2. If the p-value is less than or equal to 1, it's divergent. So this thing diverges. Let's look at 35. We have 1 over 1 plus 1 over 2 root 2 plus 1 over 3 root 3 plus dot, dot, dot. Oops, sorry about that. Let's rewrite it as a sum. I'm going from I equals 1 to infinity of 1 all over, and this is the tricky part, is, it's I root I. But then you can rewrite this as a p-series. It's the series from I equals 1 to infinity of 1 all over I to the 1 times I to the 1/2 is I to the 3/2. Okay, so here the p-value is greater than 1, so this one is convergent. So this p-series, p is 3/2, and it's convergent. Okay, so good stuff. Usually they have us prove these facts here for you. It's not hard to do. You use the integral test, basically. So, we're trying to figure out which of these series converge. So you use the integral test, and you consider the function f of x equals 1 all over x to the p on the interval from 1 to infinity. This interval, it's continuous, positive, and decreasing. Just take that for granted. So we jump to our integral. And there's two types of integrals that can pop out of this. You either do a power rule or you have to do a log. If p is equal to 1, it's a log. So first, we kind of consider the case when p is equal to 1. Okay. And we're going from 1 to infinity using sort of the engineering notation. Usually I like to put the limit out in front, and just change the bounds from 1 to b as b goes to infinity. But I see a lot of engineers do this, and I don't see any reason why you shouldn't bother. But as ln goes to infinity, ln of infinity is basically infinity, right? So if you keep putting in bigger x numbers into ln, that'll be infinity. And of course, this form is infinity minus L, so that'll be infinity. In other words, it's divergent. And of course, that's the harmonic series. Okay. Then secondly, if p is not equal to 1, and we're considering p has to be greater than 0, I believe. We say greater than or equal to 0. Let me look at my notes. I mean, if p was equal to 0, this would just be 1. The integral of 1 from 1 to infinity has to be infinity, so that'd be divergent. Okay, so let's just consider, well, obviously, I guess you could say it's divergent if it's greater than or equal to 0, but I don't know. So let's just say p is not 0. Right, so I'll integrate it using the power rule this time. Okay, so this will be, I don't know, the integral x to the negative p dx, and then that'll be add 1 to the old exponent, so negative p plus 1, or in other words, 1 minus p, all over 1 minus p. We're evaluating from 1 to infinity. The deal with this guy is the convergence will depend on the exponent. So it depends on the p-value, and there's two cases there. So there's two subcases in this subcase part 2. Either p is, either 1 minus p is less than 0, in other words, p is greater than 1. And in that case, this exponent will be positive, and this thing will just shoot off to infinity, right? So this case will be divergent. The other case is when 1 minus p is greater, sorry, I should say when this is negative, that's what the implication would be here. If this was negative, the entire numerator would drop to the denominator. And as x goes to infinity, the denominator would get huge. You'd have L over infinity, which would be 0, which would be convergent. Sorry about that. So it's the case when 1 minus p is greater than 0. When this is positive, that this numerator will blow up on you. So when p then is less than 1, you have divergence, which is exactly what we were saying in the beginning. If p is less than or equal to 1, but greater than or equal to 0, or rather, we're just saying greater than 0, because if it is 0, it is divergent. But I guess we can include that, right? So, okay, let's include it. If p is less than or equal to 1, but greater than or equal to 0, it's divergent. If p is greater than 1, it's convergent. And that's the conclusion of the p-series material. Okay? Okay, please don't abuse your notation like I was. Again, I'm having laryngitis issues, and I'm kind of trying to just minimize my work here. I mean, I can do it, but I kind of don't want you to abuse your notation. Next thing you know, you're making up your own notation. And, if I have to grade 100 people and everybody's doing their own thing, it's kind of a nightmare. We want everybody to be creative, and we want you guys to think for yourselves, but then we have to turn around and assess you, and it becomes impossible to assess 100 different individuals who are all doing their own things, unless I basically give up having a life, which okay, I'll shut up. All right, thanks for watching. Bye.